All right, now let's continue our discussion of biology. We left off with a discussion of the Big Bang and the origin of elements and some of the basic parts of those elements. We know that we forge bigger nuclei with the gravity of stars or the detonation of supernovas, which is pretty impressive, which means that we and everything we see and touch is made of the pieces of dead stars. So don't ever say you're not special, because you're made of stars, for crying out loud. Isn't that awesome? Okay, so let's move on. If I can get my computer to work here. Okay, so another thing I want to introduce then, we talked about atoms and how atoms have, in a typical atom in the periodic table, the number of protons equals the number of electrons. And you can figure out the number of neutrons by finding the difference between the atomic mass and the atomic number. But in reality, there's some variation here, known as isotopes, atoms of an element with varying numbers of neutrons. For example, we can have carbon-12, which is the atomic mass of the carbon, the typical carbon, the most abundant carbon, and we can have carbon-14, which has an extra couple of neutrons. And so that's why the atomic mass of carbon on the periodic table is 12 point something something, because they average the two together here in terms of how abundant they are on in the environment, essentially. So we get a 12 point something. But carbon-14 is somewhat common. I mean, it's around, but it's unstable. It throws off energy, and it throws off subatomic particles, and it decays over time, not into carbon-12, but it actually decays into nitrogen. Now this is really cool though, because we know how much carbon-12 there is in the atmosphere and in the environment. We know how much carbon-14 there is in the environment, and it of course decays into nitrogen. So when we find some archaeological artifact or a preserved mammoth or something, we can look at the ratio of carbon-12 to 14 in that organism, and we can tell how old it is, because carbon-14 decays into nitrogen at a rate that's predictable. So that's how carbon dating is possible. But isotopes are elements that have varying numbers of neutrons. Okay. Now, I mentioned energy levels already, and I want to introduce them more formally here. Electrons are found at various distances from a nucleus. Okay, and these are called energy levels, because the closer you are to the nucleus, the lowest energy that electron has. So electrons have energy associated with them, and if they're way out here, they have a lot of energy. If they're way down here, they have less energy, and they can change energy levels. So if an electron absorbs energy, like sunlight energy in the case of an electron involved in photosynthesis, it will gain energy and change position, and maybe even gain so much energy that it's lost from the atom. So electrons can also lose energy. Like when you light something on fire, electrons are pulled from hydrogen closer to oxygen. They're pulled closer to a nucleus, and energy is released. So when energy is lost, it's released as heat into the environment. So energy is gained or lost by these electrons, and that can cause pretty drastic effects, like fire, for example, when electrons change position. Now, within these energy levels are the actual orbitals, or where you're likely to find an electron. And a lot of the first couple of these orbitals are spherical, and then they get to be kind of this teardrop shape. And I'm not going to go into all of that. I'm going to let chemistry take you further down that road. But the energy levels are how much energy the electrons have, and then we know that different energy levels have different numbers of orbitals and different shapes in their orbitals, and that comes into play a lot in your chemistry courses. But what I do want to talk about is how these things stick together then, how these atoms come together to make molecules. And this happens with chemical bonds. And there's a couple kinds of chemical bonds. Here we have two hydrogen atoms, and we see they have these this cloud around them. This is the electron cloud. This is where their electron is bouncing around rapidly. And here we see these two atoms drawing closer and then sharing an overlapping cloud, and now they have formed molecular hydrogen, or H2. this, where they share, I didn't mention this before, but when you have, remember how I mentioned the outer energy level will have, or the outer energy shell would be another way to put it, has up to 8 electrons, or in the case of something like hydrogen, up to 2 electrons, because it only has one shell. This is known as the valence shell, that energy level, or the valence energy level, if you want to think about it that way. But the valence shell, or the anyway, this is that outer level, and when you have that overlapping with another atom forming a bond, it's called a covalent, because they're sharing their outer electrons. Covalent bond. And I'm sorry if you're hearing lots of noise in the background. My kids playing Hungry Hungry Hippos or something. Okay. All right. So electrons can be shared among atoms, and they share unequally sometimes. So some atoms are more electronegative than others. This is a periodic table that shows you how electronegative some things are. And notice in red are some of the most electronegative atoms, and that includes oxygen, which is the most important one for this semester. Electronegativity is a measure of how much attractive force a particular atom has for electrons, how much it likes to borrow them. And so in the case of, like, here we have hydrogen stuck to chlorine, right? And you can see chlorine is also red. So when these two share an electron, chlorine is able to borrow them more from hydrogen than it's willing to share with hydrogen. So it borrows them more often. And because electrons are negative and hydrogen's electrons are hanging out with chlorine more than chlorine is sharing with hydrogen, that makes this side of this molecule a little bit negative. See this little like sigma symbol? That means partially negative. It means it's not really strong charge, but it means it's a little bit more negative because this negative electron is hanging out over here more than it's hanging out over here in this bond. And that's where electronegativity becomes very important, and making molecules slightly charged or slightly polar being the word we might use for that. Okay, so covalent bonds. This is when we share electrons between atoms, okay? Now, in nonpolar bonds, that's when we have atoms of similar electronegativity sharing electrons. Why are they sharing electrons? Because they're filling their outer energy level. So, for example, let's just draw this down here. So here's carbon. And I drew carbon before. You know that carbon has 2 electrons in its first energy level, its first shell, and then it has 4 in its covalent shell, in its valence shell, its outer shell. It could use 4 more to have 8, that octet rule. Well, how could it do that? Well, here we can see hydrogen has 1 electron, and it would like to have 2. So if we take 4 hydrogens and we overlap them here, and they donate their electrons, boop. It's kind of crudely drawn, of course, as you've come to expect. But we now have a carbon that has 8 electrons in its outer shell and hydrogens that have 2 in their outer shell. They're all happy. And carbon and hydrogen have similar electronegativities, and therefore they share electrons equally, and this is said to be a nonpolar covalent bond. A nonpolar bond. Something like methane would have this, or something like vegetable oil has a lot of these nonpolar bonds. Okay, now sometimes you get a molecule formed when you have polar covalent bonds. Polar covalent bonds occur when you have a molecule that is formed from atoms that have different electronegativities. For example, you might have oxygen stuck to a hydrogen. In this case, the electrons hang out with oxygen more than with hydrogen. This is going to be a little bit negative. This is going to end up being a little bit positive in relation to that because the negative electrons hang out with oxygen more often. In this case down here, we don't have, we actually have 2 atoms stuck together, 2 kinds of atoms with different electronegativities, but sometimes we get a molecule that's not polar that results because the charges here balance each other out because there's an oxygen on each side. But usually we end up with a polar molecule that results of this. So the polar bond leads to a polar molecule. It's an emergent property. One other thing just to remind you, electrons lose energy when they get pulled close to an electronegative atom. Therefore, oftentimes heat is given off when you make these bonds. And if the electronegativity is really, really different between the two atoms, sometimes one atom will steal the electron of another rather than borrow it. So lots to learn when you take your chemistry classes. So here we see some, oops, that's awesome. Thank you very much. Okay, here we see some different molecules formed. Here's a molecular hydrogen formed when a hydrogen sticks to a hydrogen. And there's two different ways to draw it. You can draw these two dots representing the shared electrons between the two, or just a single line. These two, when you share an electron, one each, that's just a single covalent bond. That's a single bond. When you share two pairs of electrons, like we see between these two oxygens, that's a double covalent bond. And that can be drawn like this. This is molecular oxygen. This is what we breathe. It's drawn like this. Each line represents a covalent bond. Here we can see oxygen and hydrogen stuck together forming water, or methane like we drew in the previous slide. So practice drawing a few of these, make sure those make sense to you. I assume to get into this class you should have had chemistry in high school, so I assume you're familiar with some of this. Okay, so ionic bonds. Ionic bonds occur when one of the atoms has a high electronegativity and it actually steals an electron from the other. Typically that's how they work. So for example, here we have sodium, and notice sodium has 1 electron in its outer shell, and chlorine has 7 in its outer shell. And chlorine is very electronegative. So instead of sharing an electron here, what happens is, and I notice you don't have to know this number, but if the electronegativity difference is greater than 1.9 in the scale they use to measure this, then typically we're going to steal electrons instead of share unequally. So I like to think of polar covalent bonds like me and my little brother sharing a toy, and I'm more electronegative. I was bigger than him. I would borrow the toy more than I'd let him play with it, right? That's kind of like sharing electrons in a polar covalent bond. But in this case, we have a sibling here who steals the toy rather than shares it. So the outer electron here is ripped off the sodium and it goes to chlorine. And what does that do? That now means there is, in the case of sodium, there are more protons than electrons, right? And here we have more electrons than protons. So that's going to change the charge of the molecule. Now we have a positive sodium and a negative chlorine. And when you have a charge like this, these are now ions. Ions are charged atoms. Atoms with a charge. A positively charged ion is called a cation. A negatively charged atom is called an anion. Now the cool thing is, just like a magnet, opposites attract. So this positive atom here is now attracted to this negative atom, and that forms an ionic bond. And we form sodium chloride or table salt when that occurs. Sodium chloride forms from this ionic bond. Okay, ionic bonds, that's how they work. The last kind of bond I'm going to emphasize in this lecture are hydrogen bonds. Now here's an example of ammonia. Ammonia has nitrogen attached here and hydrogen attached here, and I want to show you that nitrogen is more electronegative than hydrogen, so the electrons in these covalent bonds are polar. This is a polar covalent bond. They hang out with nitrogen more than hydrogen. That makes hydrogen positive and nitrogen a little bit negative, partially negative. Same thing with water. Electrons hang out with oxygen more than they hang out with hydrogen. That makes hydrogen a little bit positive and oxygen partially negative. So now, just like in an ionic bond, we have a weak attraction here. We have a positive and a negative interacting, and that creates a bond. But in this case, there were no electrons stolen, and this is actually weaker than an ionic bond. This is the weakest bond of the bunch that we've been talking about. This is called a hydrogen bond. Okay, hydrogen bonds occur between molecules, and it's due to the unequal sharing of electrons within the two molecules. Okay, hydrogen bonds. All right, so your book will also talk about van der Waal interactions, which are even weaker bonds than hydrogen bonds. Worth knowing about, they are important. I'm not going to emphasize them in this lecture, but you should read about those and at least be familiar with their existence. When we pick up, we're going to continue with a discussion of structure and function and chemistry.